Hello and welcome to MyScience Tutorials. In today's video, we are going to be looking at reactions of alkanes. So without wasting my time, let's get started. Now, alkanes are generally unreactive, okay? So they normally tend to undergo a reaction we call substitution reaction. So what causes this unreactivity on the part of alkanes? Now, alkanes, let me give the simplest example, which is a methane, okay? The bond between the carbon and then the hydrogen that we are seeing over here, okay, was as a result of an easier or head overlap between what the orbitals of the carbon and then the orbitals of hydrogen. Now we know easier or head-on overlap. This overlaps leads to a very strong, okay, a very strong bond, okay. So as a result, the carbon hydrogen bonds over here are very strong that before we break them we need a very high energy to break this bond, okay. So because the single covalent bond formed in alkanes are so strong, they require very high amount of energy to break them, okay. So because this energy is so high that normally it is not attained during reaction mechanisms, these bonds cannot be broken, okay. So the only thing that can be done over here is for what one of the hydrogens or more of the hydrogens to be substituted, and then when this substitution occurs, we then tend to call the reaction that occurs, okay, substitution reaction. So for example, maybe we have let's say a compound B here, okay. So in the process we will have compound B replacing the hydrogen over here, so we'll be having this, okay, this is 3 attached to compound B, and then we will be having HB as our byproduct, okay. So this is a typical example of what a substitution reaction, a reaction we are calling substitution reaction. Now this is the reaction that alkanes undergo, and then yeah, so what is the substitution reaction in the first place? So this is a reaction in which an atom or group of atoms, okay, is replaced by another atom or groups of atom, okay. So we have an atom over here. When we replace it with another atom, then it becomes what? Substitution, because we could see at the end the bond over here is not broken, only the atom at the edge over here is being replaced by another atom. So this reaction can be called substitution reaction. Now alkanes undergo halogenations, okay. They undergo halogenation, that is we can add the halogens to them, that is we can add chlorine, bromine, and even iodine to them, okay. So they normally tends to undergo halogenation, okay. So in this tutorial video we are going to look at how the halogenations of alkanes actually occur in the presence of UV light. Okay, so now halogenation of alkanes undergo substitution reaction with halogens, okay, to yield haloalkanes and hydrogen chloride, okay. So what we mean by haloalkane is just an alkane group, let's say CH3, okay, attached to a halogen, okay. So this is a haloalkane, okay. So this a typical example of a haloalkane, and then plus what HCl or what HBr, depends on the type of halogen we use in the reaction. Then we will either be getting HCl or HBr as the byproduct. Now this reaction, okay, it occurs in the presence of what? Sunlight, okay. We need sunlight or UV light, okay, for this reaction to occur. So assuming you want to carry out a halogenation of an alkane, and then you place your reaction vessels, okay, or in the dark, you place it in the dark, the reaction will not occur, because the initial stage of the reaction requires the presence of sunlight to be able to be carried out, okay. So without the presence of sunlight or UV, the reaction will not occur. So before we look deeper into the reaction mechanism that goes into the halogenation of alkanes, let's have a look at the various types of bond cleavages that occur, or bond breakages. Now there are two types of bond breakages, okay. So we have one, the homolytic cleavage. We have the homolytic, and then two, we have the heterolytic. Now the homolytic cleavage, okay, the first one over here, this is the bond breaking where an electron from the bonding pair in the bond is equally distributed among the atoms. Okay, so what we mean by this, okay, is that in homolytic cleavage, let's say we have atom A attached to atom B, okay, the electron pair we have over here, the bond that we formed over here has what? An electron pair, that is 2 electrons. Okay, so in homolytic cleavage, when this bond is going to break, the electron over here, one of them will be given onto this atom, and then the second one will be given to this atom. So at the end we'll be forming what? Radicals, free radicals. Okay, so this is a typical example of what? A homolytic cleavage. This is an example of how, or this is how a homolytic cleavage occurs. Okay, now mind you, do you see how I use the arrows? I use a half arrow. Okay, this is to show that the transfer of electron is not complete, it's partial. Okay, so it means the electrons in the bond over here are being shared equally between the atoms that are connected together. Now in heterolytic cleavage, okay, the second one, the opposite of this happens, in the sense that the atom that is most electronegative tends to have all the shared pair of electrons being put onto it. Okay, so assuming we have, let me use the same example, A and B, and then let's say B is more electronegative, sorry. So it means the shared pair of electrons over here, both of them will be moved onto B. Okay, so in this case we will be forming what? Cation. We will be forming A plus, and then we'll be forming what? B minus. Now in this case, the A is now what? When it is an organic compound, okay, and this occurs, we call it a carbocation. Okay, let me use a well-defined example. So assuming we have methane, okay, so we have CH3 attached to H, this methane, okay, undergoing a heterolytic cleavage. It means all the let me use methyl bromide. Okay, this is a perfect example. So in this case, the shared pair of electrons is being put onto the bromine. Okay, so at the end we'll be getting what? A methyl cation plus bromine anion. Okay, so in this example, the methyl cation over here is what we call as what? A carbocation. Okay, this is a carbocation, that is a carbon bearing a positive charge, so it's a cation, and then it's carbon is the one bearing the charge, so it's carbocation. Okay, so these two forms of cleavages are really important when we are dealing with what? Halogenations of alkanes. So now that we know the types of bond cleavages that occur, and then what are formed at the end of each cleavage, let's go. Okay, in homolytic we form what? Free radicals. Okay, free radicals. And then in heterolytic cleavage you form carbocation. Now the free radicals that have been formed over here, they are really reactive. Okay, so because they have an electron over here, and then electron is needed for reactions to occur, so they are really reactive. Once it starts, then they continue, they just go like that. It's really amazing. So let's have a look at the mechanism of halogenations of alkanes, and then you get to appreciate what I'm talking about. So we are going to look at what? Halogenation of what? Of alkanes. All right, so the general reaction that we normally write is, assuming we have methyl again, methane, which is the simplest alkane ever, plus chlorine molecule. Okay, this will give us what? CH3Cl, okay, methyl chloride plus HCl. Okay, so this is an example of what? A substitution reaction, specifically halogenation or chlorination. Okay, so this is what? Chlorination. This is chlorination of alkane. Okay, now this chlorination, okay, this is just the overview. This is just how the reaction proceeds, but how the chlorine tends to attack the methane, okay, to now have a methyl chloride and then HCl occurs in 4 steps. Okay, so let's have a look at these steps. Okay, so the first step, which is step 1, is what we normally call the initiation stage, or the initiation step. Okay, now this is the step that requires the use of the sunlight or UV for it to occur. That is the more reason why if you carry out this experiment in the dark, it will not occur, because the radicals that are needed to start the reaction occurs in the presence of sunlight. Okay, so if you put them in the dark, they will not be produced, and then the reaction cannot proceed, will not even start in the first place. So let's have a look at what happens. So in the initiation step, okay, we have the chlorine molecule, okay, Cl attached to another Cl, okay, in the presence of what? Sunlight, okay, sunlight or UV. Okay, you can just write sunlight or UV, undergoing what? A homolytic cleavage. Okay, so it means an electron will be given here, one electron, and then another one will be given to this chlorine molecule over here. So we'll be forming what? Chlorine radicals. We'll be forming chlorine radicals in the first stage, which is what? The initiation step of this reaction. Now step 2. Okay, now step 2 and step 3 are called what? The propagation step. Okay, so propagation step. Okay, now in the propagation step, what happens? One of the radicals over here, the free radicals, now attacks the methane that we have over here, okay, to now form something. So we have the methane CH3 attached to an H, okay, plus the radical. Then what happens? Okay, now the radical over here picks up the hydrogen over here and then gives the electron to the alkyl functional group that is being put, which is the methyl. Okay, so at the end we'll be getting what? We have CH3, then the radical, this electron over here is being given to the CH3, then plus the HCl. Okay, so the chlorine will pick the hydrogen over here, so we have HCl. Okay, so this is the second step, is the step in the reaction mechanism where the HCl is produced, what we have over here as the byproduct. Okay, so that is where the HCl is being produced. Now once we have the CH3, which is the methyl radical in solution, then we go to step 3, which is also what? The propagation step. Okay, then this, now the methyl radical CH3 dot, okay, now attacks a new molecule of what? Chlorine. Now we know this doesn't mean we have just one chlorine molecule in the solution. Okay, so just one mole of what? Chlorine contains what? The Avogadro's number of what? Atoms. Okay, so it means when we have looking at the Avogadro's number, is quite a huge number. Okay, so which means when we use 1 mole of chlorine, it means we have the Avogadro number of what? Chlorine molecules, which is very much, like, it's plenty. Okay, so the methyl radical over here now attacks the chlorine molecule, okay, another chlorine molecule in the solution to form what? CH3 Cl. Okay, over here the chlorine, the methyl radical attacks the chlorine, okay, picks one chlorine and then give the electron to the second chlorine in the solution. Okay, so we now have what? Chlorine radical being produced again. Okay, so up to over here, okay, this is where we get what? Our product, which is what? The alkyl chloride, okay, or the haloalkane. Okay, so this is in the second step, we get the byproduct, which is the HCl, and then in the third step we get our product, which is the main product that we are after, haloalkane. But then what happens? Let's take a look at this. Because we still have chlorine molecule, okay, chlorine radical, sorry, we still have chlorine radical inside the solution. It means this mechanism, okay, or this reaction can continue further. Okay, so let me read something very, very important for you. Now, if the methane molecule is not in excess, which means what? If we have what? The methane molecule as what? As the limiting reagent. If we have the methane as the limiting reagent, which means it is not plenty or it is not many. Okay, if we have the methane molecule not in excess, okay, it means what? step 2 and step 3 can be repeated to give us what? Di, tri, and what? Tetrachloromethane. Okay, so it means if we have this, okay, in limited amount, okay, if we have this, the CH4 in limited amount, something interesting happens. Okay, so after we form the CH3 Cl, it then now reacts with the chlorine radical formed again. So normally this is where the reaction stops. Okay, we get our product and then we get the chlorine radical. Okay, but then if the question tells you you have the methane molecule, okay, as the limiting reagent, or it's not in excess, it means what? The chlorine radical again, because of its being a radical and it is very reactive, like I said, will then attack the haloalkane again to form another product. So it will attack again, then pick one hydrogen and then give the electron over here to the haloalkane. So we'll be forming what? CH2 Cl radical plus HCl. Okay, then from there let's call this step 4. Then from there, then step 5. Okay, then step 5, we have the CH2 Cl radical will now attack a new molecule of what? Chlorine. Okay, to give us what? CH2 Cl, which is dichloro what? Methane, plus Cl radical again. Okay, so you could see at the first part we over here, we have what? Chloromethane. But then if the methane is in limiting reagent, okay, or it's not in excess, okay, the reaction will continue to step 4, where we will have what? We will form the CH2 Cl radical again, and then if that occurs, okay, this now becomes a radical which is very reactive, and then it will now go and then attacks a new chlorine molecule to form what? Dichloromethane. And then this further continues because we still have chlorine radical inside the solution. Okay, so this will continue until we get what? Trichloromethane, and then at last we get what? Tetrachloromethane. Okay, so this reaction is said to be what? A chain reaction. A chain reaction in the sense that once the reaction starts, okay, it continues on its own. Okay, so after the radicals are formed over here, after the radicals are formed, if you now put the reaction, let's say in the dark, the reaction will continue because the chlorine radicals are already produced. So the first step is the only step in the reaction that needs the sunlight. Okay, sorry for all the background noises. So the first step in the reaction is the only step that needs the sunlight. After that, the other steps, okay, do not need the sunlight. In the absence of the sunlight, they can still continue to produce our product, which is a haloalkane. Now on the other hand, if the methane is in excess, then the chlorine free radicals, okay, attack a fresh methane molecule as shown in step 2 and step 3, okay, to give us what? A repeated chloromethane. Okay, so assuming we have CH4 in excess, okay, if we have CH4 in excess, it means after we are done over here, okay, this chlorine radical will not attack this product anymore. It will not go and attack the new methane molecule in solution to give us what? Another chloromethane. So we have what? Chloromethane produced in excess. Okay, but in the absence of what? Excess methane, they will be forming what? Dichloromethane, trichloromethane, and then tetrachloromethane. So this is how halogenation of alkanes occur in the presence of sunlight. So I hope you've learned something, and this video actually helps you know how to go about with your halogenation of alkanes. Okay, so this video is just a quick overview of the halogenation of alkanes. So I hope you learned something. So thank you so much for watching, and then I'll see you in the next video. Bye bye.